Okay, so the next one is exercise 10. It has two parts. In the first part, we are given a unique factorization domain R and a non-zero polynomial fx has been chosen over R. We have to prove that such a polynomial can be factorized as a product of an element A in R and another polynomial f1x again over R, which is primitive. And in the second part we have to prove that such a decomposition is unique up to associates. And this is one thing we have already, this fact we have already used in one of the proofs in the text. So let's see the solution, which we start with something we already know. We already know that fx can be written as the content of f times some polynomial f1x, where f1x is some polynomial over R. Now note one thing carefully, that since the given polynomial fx is non-zero, so that means not all of its coefficients are equal to 0, and that is why their greatest common divisor exists in R, which is nothing but the content of f. Now our aim is to prove that this f1x is a primitive polynomial, that is its own content is 1, is the unit element 1 in R. To the contrary, suppose that that is not the case. Suppose content of f1 is not equal to 1. Okay. Now, since fx is non-zero, f1x is also non-zero. That means not all of its coefficients are 0, and that is why in fact the content of f1 exists, which itself is a non-zero element of R. Now the fact that we have supposed it's not equal to the unit element also makes it a non-zero, non-unit element in R. You may wonder how this condition implies that this is not a unit in R. You may think that okay, it's not equal to the unit element, but it may itself be a unit in R. However, that will not be the case, since we know that this is a GCD of some elements in R, and in R, GCDs for the same given elements, there are multiple GCDs which are obtained by multiplying by unit elements, and they are all associates. So the condition that this is not equal to 1 also means that this CF1 cannot be a unit, because had it been a unit, say if we have CF1 equal to U, where U is a unit in R, then multiplying this GCD by U inverse, you get another GCD which is associated with this one, which also can be taken as content. You then get the statement that 1 is the GCD of f1x, which contradicts this supposition. So the supposition that this is not equal to 1 also means that this thing is not a unit. So that means this CF1 is a non-zero, non-unit element in R. then CF1 is a non-zero non-unit, I should not say non-unit element, but a non-unit in R, and hence has a, or we can write like this will be better, and hence there exists a prime element Q in R such that Q divides CF1. But CF1 being the content of F1 already divides all the coefficients of F1x. So Q will also divide all the coefficients of F1x. Thus, Q divides all the coefficients of F1x. So that means if we take Q common out from all the terms of F1x, we will have a decomposition of F1x itself like this, where Gx is that polynomial over R which is left when you take Q out from all the terms of F1x. We thus have so we can use this that decomposition here and write fx equal to CFQ times Gx. So you can now see that all the coefficients of CF are divisible by all the coefficients of Fx are divisible by this ring element CF times Q. Thus, all the coefficients of Fx are divisible by CF times Q. If you are having difficulty believing that this is true, you just think of it like this: Fx being a polynomial over R has terms which have powers of x multiplied by some ring elements from R. On the right side also you will have one such polynomial. This equality tells us that the corresponding coefficients should be equal. From there you can conclude that CFQ divides all the coefficients of Fx. Okay, now because CFQ, a ring element, divides all the coefficients of Fx, so it will also divide their greatest common divisor, the GCD of all the coefficients of Fx, which is nothing but CF. Since, in fact, let's just write all the things. Since CF is a greatest common divisor of all the coefficients of fx. So we have this divides C F. Hence CF is some K times CF times Q for some ring element K. Okay, since CF is being the content of some polynomial, since CF is non-zero and R is an integral domain, we have from the last equation above this equation, you can cancel CF from both sides. 1 equal to K times Q, but this proves that Q is a unit in R, which contradicts the fact that Q is actually a prime element, because a prime element by definition is it is not a unit. This implies Q is a unit in R, which is a contradiction. So our supposition is wrong. That means that is CF1 must be equal to 1. Hence F1x is a primitive polynomial. We have shown what we wanted to show in part A. Now we move to part B. In part B, we have to prove that this decomposition is unique. So let fx equal to a times f2x, where a is some non-zero element in R. A has to be non-zero because fx itself is non-zero, and f2x is a primitive polynomial over R. That means an element in Rx which is a primitive polynomial. Okay, then just like this step, A divides all the coefficients of fx, which we can see from this equation, which implies A will divide their greatest common divisor, which is the content of f. So this is one thing we are getting from this equation. So that means since A is dividing this, so this will be a multiple of A. Where H is some element in R which of course is itself non-zero. We thus have okay, now if we use this in the original decomposition of f, so then we will have what? Originally f is decomposed like this, cf1 or cf times f1x, the decomposition that we have from part A. Fx equal to A times f2x. Oh, so okay. Now here itself we can use in place of CF we can use HA. Okay. Yes. Okay. So let us write it like this. This is equal to, or okay, I should have, excuse me for this mess up. I should have started with this. HA f1x is equal to, HA is CF, f1x, this is equal to fx, and fx is A f2x, and due to the fact that A is non-zero, A of course is non-zero, and R is an integral domain, so you can cancel A from both sides. We have, so if we cancel A from both sides, we will have this H f1x equal to f2x. So we are ending up with this equation. So And from this equation again we get the fact that h divides all the coefficients of f2x, since f2x is primitive and we can write like this, since f2x is primitive, we thus have, since h divides all the coefficients of f2, so h will divide the content of f2, which is a GCD of all the coefficients, and since f2 is primitive, that content is equal to 1 or a unit, same thing. But this implies h is a unit in R, because h is dividing 1, so 1 will be a multiple of h, which just means that h is a unit in R. Now from here we can conclude the thing that we want, namely uniqueness up to associates. There are two things to note. One of them is this equation, and the other is this equation. Now CF equal to HA implies that CF and A are associates, and HF1x equal to F2x implies that the corresponding, we can argue like this, that the corresponding coefficients of f1 and f2 are also associates, because the corresponding coefficients of hf1 and f2 are equal. So that's why the corresponding coefficients of f1 and f2 are associates. We can either write that, or we can at once write f1 and f2 are associates in Rx. In fact, that I think that will be better, implies that f1x and f2x are associates in Rx, keeping in mind that this unit H in R is also automatically a unit in Rx. Note that the unit H in R is also a unit in Rx. So that's how we have uniqueness, that the two decompositions of fx, one as content of f times a primitive polynomial and another arbitrary such decomposition where we have a ring element A and again one primitive polynomial. This decomposition is unique up to associates. That means the only difference between CF and A is that they differ by a unit in this sense, or in other words they are associates. Similarly, in Rx, F1x and F2x are associates because they are also differ by a unit. In fact, we now see that that unit is in both the cases the same element in the ring R. So this completes the solution. Next we have exercise 11. If R is an integral domain, and if F is its field of quotients, okay, prove that any element Fx in this polynomial ring Fx over F, which is the field of quotients of R, can be written like this. Can be written as Fx equal to F naught of x divided by A, where F naught of x is actually a polynomial over R and where A is a non-zero element in R. In fact, you can understand this exercise better if in place of R you take the integral domain of integers, and then in place of F you will have the field of rational numbers. So a polynomial over the rational numbers can be written as a polynomial over the integers divided by another integer. Okay, so let we start by actually writing the terms of the polynomial fx. A naught plus a1x etc. plus an x to the power n, where these coefficients are coming from F, the field of quotients of R. Now since F is the field of quotients of R, so each AI can be written as a quotient of two elements from R. Since F is the field of quotients of R. We have for all I lying between 0 and n, AI equal to BI divided by CI. For some BI comma CI belonging to R with, of course, CI not equal to 0. Then this can be written like this: B naught divided by C naught plus B1 by C1 times X and this is equal to plus B1 Cn minus 1 times x to the power n. I hope it's visible and you understand what we are doing here. Which is equal to this, where and A is equal to C0, C1, etc. to Cn. Since each Ci is non-zero and we are in an integral domain, so their product is also non-zero, that is A is non-zero. So this completes the solution. It's a simple one. This is also something we have used in one of the proofs in the text. Okay, then Exercise 12. Prove the converse part of lemma 3.11.4. Okay, let us briefly recall what this lemma states. It states that, say we have a primitive element fx, a primitive polynomial fx over R, where I think R is an integral domain and f is its field of quotients. Then this is irreducible over R, or irreducible as an element, or let me just say it in the order in which it has been said in this lemma. It is irreducible as an element of fx if and only if fx is irreducible as an element of Rx. Okay, so we have already proved that if fx is irreducible as an element of Rx, then it's also irreducible as an element of fx. That is the hard part that we proved in the text. Now we have to prove that if it is irreducible as an element of fx, then it is also irreducible as an element of Rx. That is the converse part, which however is just something new. It's almost obvious we have to write that thing. Since Rx is a subring of fx, irreducibility of fx as an element of fx automatically implies irreducibility of fx as an element of Rx. And why is that so? You see, when we are saying that fx is, this small fx is irreducible as an element of fx, that means if we are able to write fx as a product of two polynomials which themselves are in fx, then one of them has to be a unit in the polynomial ring fx. So that means fx cannot be reducible over R. In other words, if in that case that fx, this small fx is irreducible over f, we are able to find a non-trivial factorization of fx as in product of a non-unit element gx and a non-unit element hx in Rx, then this will also be non-unit elements in fx, and hence this will be a non-trivial factorization of fx in fx also, contradicting its irreducibility of fx over f. So that's why we are writing this thing. And there is something to note here. It's that in the original statement of this lemma, we need primitivity of the polynomial to prove the part that is converse to this one, that is the original one. However, in this converse part, we don't need that primitivity. Note that we don't need primitivity of fx here. So that is the solution. Then exercise 13. Prove corollary 2 to theorem 3.11.1. Which also, let us recall what that corollary is. It says that if f is a field, then this polynomial ring in several variables is a unique factorization domain. Now, the corollary says that this theorem says that if R is a unique factorization domain, then so is Rx, and applying this a finite number of times, any finite number of times, we get the first corollary 1 to this theorem, that this polynomial ring is also a unique factorization domain. So that means here if we can show that our field is a unique factorization domain, then automatically by corollary 1 this will follow. So that's why we write the solution like this. In fact, I think that's what we have written here. All we need to prove is that f is a UFD. It's enough to prove that f is a unique factorization domain. This we can do by noticing that F is actually a Euclidean ring, and since every Euclidean ring is a unique factorization domain, so F is also a unique factorization domain. Now I can't remember if I have actually demonstrated this fact that every field is a Euclidean. Let's just do it here. We show that F is a Euclidean ring. For that we need a D function. Define D from F minus 0, because the D function is defined only for non-zero elements in a ring. From this into the set of integers by D of A equal to the integer 1. That is, D is the constant function mapping all the non-zero elements of the field F onto the integer 1, the positive integer 1. Then for any A and B belonging to F minus 0, we trivially have D of A which is equal to 1 is less than or equal to 1, that is D of AB. So that is the first condition for the D function to be a D function actually. Also, okay, so then we have to be able to say divide A by B to get a quotient and a remainder, which in this case we can easily do. Divide A by B. Our quotient is AB inverse. Note that since we are in a field and B is non-zero, so its multiplicative inverse exists, plus 0. So here our quotient is AB inverse and remainder is 0. This shows that F is a Euclidean ring. That means every field is a Euclidean ring in a somewhat trivial manner. Hence, F is a unique factorization domain. We have already proved in the theory of Euclidean rings that every Euclidean ring is a UFD, a unique factorization domain. And consequently, by corollary 1, corollary 2 follows. Okay, now we come to exercise 14. We have exercise 14 and exercise 15. Exercise 14 has a somewhat vast solution, so it would be better if we do that in the next video. I know you are waiting, some of you are waiting for field theory. Just give me one more video in ring theory and then we will move on to field theory and vector spaces. So with this I end this video on rings. So see you in the next part. Until then, it's me Lucifer from a mathematical room. Have a nice night.